Hi everyone, welcome to the 978th monthly meeting, and we have a speaker here, Mackenna Wood. She is talking about a very interesting topic, murder in the observatory and the enigma of stellar ages. So we have something very exciting going on outside too. We were seeing some aurora, so if we get a chance, we can take a look at it after the meeting. With that, I'll go straight to the agenda. Now, Glenn.
Is Rich with us? Rich Nugent?
He's not able to make this
I
meeting.
thought he said he will join on.
He's going to try to get on Zoom.
I don't see him.
Okay, well, he was going to give a lot of this, and because we have an aurora going on, we'll go through this fairly quickly. You all read the poem? Let's go to the cartoon. Next slide, or did we already go past it? There was a slide, I think, before this.
Yes.
Some of you may appreciate that. Okay, now the poem. And so Rich isn't here. We'll go ahead now. We'll go to the next slide, and there we go. There was a partial lunar eclipse on 17 September, and this is a picture that Rich himself took. How many of you did get to look at the eclipse? Again, it wasn't anything spectacular. I just stepped outside. If you know what's going on, just check it out. Something to do. Okay, next slide. Venus in 2024. Well, I think the slide is saying, hey, we got an aurora going on. We want to get to our guest speaker here. All right, that's what Venus is doing. It's in the sky. Next, and I don't mean to diminish what Rich had, but he told me he was going to be in here and I didn't even rehearse any of this. So, but Venus is making its nighttime appearance now. That's the good news. What's it at maximum? Right about February, it'll be up at its highest. Now, I know it's not a very favorable apparition in the evening sky. It's not as high as it could get other times. Okay, next slide. Mercury Superior Conjunction, September 13th, greatest elongation east. Saturn, September 30th. What did I say? 13th. A old man talking. Saturn's was on opposition on September 8th. Neptune trans 11 o'clock. Uranus rises at 7:45. We'll go on to the next slide. Mars currently rising about 10:30 p.m. EDT. It's still kind of more of a morning object. Jupiter also in the morning, but getting closer to midnight now. That's going to be starting in the evening sky. And I could not gloss through this. Saturn is nicely placed right now, so that's the one you really want to look for. It's in the evening skies. Next slide. Spike occultation, November 27th, just before 5:30. Now, as I understood, is it an occultation? Yeah, it is an occultation in the morning sky. And again, I haven't heard any particulars. Anybody know, is this supposed to be a favorable one, or is this going to be very low?
If it's November with Spike, it's probably going to be really low.
Yeah.
That says altitude 16 degrees.
Yeah, so unless you have a really good horizon there. All right, next slide. All right, Comet Tsushinsan Atlas 2023 A3. It will be in the evening sky in another couple of days. And we're not sure. I think it has safely passed the sun, am I right? It didn't get disrupted or anything? So it should be a very bright object. Just start looking in the evening sky after sunset. And I'm sure, I'll tell you what, I do a lot of cases. I just go to the website, I look at the ATMoB emails, and if something is going on, somebody is seeing it, and somebody's going to be saying something. So if you see about 50 pictures of the comet, you missed the first night. Yes, Joe?
-3.
-3. Well, there was a comet Kohoutek that was supposed to be -7. All the old people are, yeah, I remember that one. Okay, next slide.
Last night, right at sunset, I didn't see anything.
Yeah. All right, again, the variable star of the month is T Corona Borealis. Again, we've been watching that. I was talking to Joseph. It's still, I haven't even seen Corona Borealis in a while now. I'm losing it in the treetops over in the western sky, but apparently still visible. You checked out with binoculars last night or tonight,
That's right.
and still wasn't visible. So, and I did look at the AV or so stats, and it's still around 10th magnitude visually. So I predict that when it's in line with the sun, you can't see it at all. It'll have its outburst. And then when it finally moves away from the sun, it'll be older. You'll have to wait another 80 years. Okay, next slide. Joseph's variable star, this is Cygni. And just had an outburst about a month or so ago, about 20 days ago, and that's about halfway through its cycle. So if it follows its 50-day approximate cycle, it should have another outburst from 12th magnitude up to 8th, sometime the end of this month, early November. So again, if you've never seen this before, check out now. It'll still be near minimum, but it'll be a chance to at least learn the field of view and so forth. And then by the time its outburst is near, you'll be able to check it out every night. It used to take me about a minute just to go outside, set up my telescope, and I could check very quickly to see what it was doing. The first time around, again, it took about 10 to 15 minutes to locate the area. Next slide. Should be the double star of the month. And this one is Eta Persei, and it's a pretty double star. The primary is kind of a K-type giant star, so you'll see kind of a yellow-orange star. The companion tends to be a bluish color. Somebody described it as kind of an, it's not quite as bright equally as, say, Albireo, but it's kind of a miniature Albireo, so give it a look-see if you get a chance. He's also showing where the Perseus radiant, so it's right up there next to the Perseus radiant. Next slide. I think we're getting to the object of the Observer's Challenge. Now, one thing, this is just a generic picture. I didn't put anything up by Doug or Mario this time because we're going to start doing something new with the Observer's Challenge, and that is we're going to be putting them on our website. And there's that picture of Mario. Is that yours,
Isn't that
Mario?
my picture?
I don't think it was. I think I was saving them again for what we're going to do is
Sure
next
looks like mine, but all right.
It could be mine as well.
Well,
Well, it has spider veins, so.
well, what we're going to do is save it for next month. We're going to summarize all of the observations. So if you haven't made an observation of M2, save it, and next month we'll summarize these on the website. But we'll also summarize them here when we do the observing committee meeting. So, but anyway, it's about 5 degrees north of Beta Aquarii, and I just went out a couple nights ago to check it out. It's very easy to find. It's visible in binoculars. It's about 6.5 magnitude. And all I did was I just aimed my binoculars at Beta Aquarii. I just went, and there's this little fuzzy patch of light. And then with the telescopes, it's the same thing. I just go to the finder scope and just go 5 degrees north. So you're not really star hopping. It's more like area searching. You know generally where it's going to be. And then just do a low power sweep if you're using a telescope. And you see that fuzzy little patch of light. With a larger telescope, 10-inch scope, it's a very pretty sight, very impressive. Next, and yeah, go ahead. We had some challenges. I remember now. I put in a new slide here. Let's go to the next slide. And here are the challenges you're going to get for Messier 2. The first one, can you see Messier 2 with the unaided eye? We'll try it in the parking lot, see if we can see Messier 2 with the naked eye from Cambridge. I wouldn't even try it where I live in Townsend. That's a rural area, but my skies are about magnitude 5. You've got to really be out in a dark sky area. We're talking a high Bortle number, and give it a shot, because it's 6.5 again. So, again, even if you have magnitude 6 skies, this might be a little bit beyond visibility. Next one, what is the smallest aperture to resolve in Messier 2? I resolved it with 10 inches. I was going to go to a 6-inch telescope, but again, sky started to cloud up. So I've got a 4-inch, a 6, and a 10. I'll try that, but that's a challenge for any of you. See what's the smallest aperture, report that in. What's the smallest aperture that you're able to still resolve its individual stars?
Can you go back to the slide that shows it, say, for the dark rift?
Well, here's the thing. Can you see the dark rift that crosses the northeast edge? Let's go back.
Yeah, what are you saying?
It's right there.
All right, there's a 10th magnitude star in the field, and supposedly it's about halfway. And I'm looking at this area
That's
here,
it.
and that's the dark rift. And when I looked at the 10-inch telescope, it was on the edge of the cluster. So I think with larger apertures, you'll see more of the stars beyond that, and you'll see it going through. With my scope, I was able to resolve about this part of the cluster. I just saw this edge was flat.
Thank you.
Okay.
That's what I want to see.
Excellent. So I did see it with a 10-inch scope, but I think, again, a larger scope, you get more of the stars on the other side of that ridge. It's kind of a nice thing to look for. And Messier 2, by the way, is one of the earliest of the Observer's Challenges. The first year they ever had it, it was in the challenge list, but it wasn't to look for that dark rift. That's why he brought it back again. You can see this time, you can see that dark rift. It's kind of like the propeller in M13, you know, how many can see it and how many can't. Next slide. I think it's just a preview. And this is something called the Derelict Galaxy Group. When I was talking about it last month, I was kind of confused. There's another galaxy group down here, but this is Stefan's quintet. This is actually a cluster of galaxies that are right around NGC 7330. You can see them up there in Doug Paul's picture. I don't know if that's going to be much of a thing I'll be able to see. I looked at the magnitudes here. I did a little quick research before I got here. And it's NGC, well, the ones are listed right here. These are the 4 galaxies you're looking for. And I think that image is pretty much oriented to what is in Doug's picture. 7331 is a bright galaxy. It should have been caught by Messier. I've seen it with a little 3-inch telescope, no problem. The other ones, though, I just got these magnitudes off of Phil Harrington's book. NGC 7335, 14.4 magnitude. Gets better. 7336, 16.8. I'm not going to see with my little 3-inch Edmund. 7337 is 15.2, and NGC 7340 is 14.7. So I don't know, maybe we'd see it from the clubhouse with the 25-inch, but even then the light pollution might give us a bit of a run for our money. But anyway, that's a challenge for November, so I'll put something out about that. But keep it in mind, if you want to get an early look, check it out when you get the next clear night. And that's it, I believe. I think, oh, Steve's not here. Was he going to have you do the observe? Okay, just a couple of things going on. Clubhouse Friday, Saturday nights. 25th to 26th October is going to be that small, introduction to the fall sky. I'll get something together for that if we have a clear night. And then these are all dark sky nights at the clubhouse. And the small scope scavenger hunt, that's coming up. I haven't really got a date yet set because I want to get the fall observing thing in first. And then we'll worry about a small scope scavenger hunt. Next slide. Okay, now Rich, did he have anything you were supposed to say or just?
I thought he was going to get it. No.
Okay. Anyway, take a look at the list. And if there's anything there that's in your area, you live in that area, by all means join in. They're very fun events. What I've been doing in recent times is bringing my little 4-inch reflecting telescope and offering the kids a chance to take a cell phone image of the moon, and then they take home a souvenir. You know, it's a little tricky because there's a nice sweet spot you got to get, but then in about 4 or 5 minutes, they usually find that you get a nice picture of the moon. So consider that as anyway, anything if you just go to one of these star parties.
Glenn?
Yes.
The one on November 7th, you have twice in Chelsea, but then the dates are 11/12 and 11/8.
You know, you'd have to ask Rich, unless there was
I think it is a rain date.
yeah,
so
that's what I'm thinking is a rain date.
yeah, so there's 2 star parties scheduled for November 7th, and the rain date for Kennedy Middle School is 11/12, and the rain date for Chelsea is 11/8.
And next,
They aren't in the same place, even though they're both in Chelsea.
you have to contact Rich about that, yeah. And the next slide. Okay, before I go, I gotta pardon my voice, and I'm kind of scatterbrained tonight. My granddaughter ran a cross-country race, and I was screaming and yelling for her, and then I'm excited about this Aurora and our speaker coming up too, so, but as I always say, just keep looking up. There's a lot to look for tonight and any clear night. Take care, and good luck. Good luck.
Any news about the new comet, the C2 2024 S1?
I heard of it. Anybody hear it? There's another one that's, what's the deal with that one?
Just that it's going near the sun, and we'll see whether it survives.
So it should become visible within the next couple days, just after sunset.
You know what, again, I tell you what, a great source is just ATMoB email, because if something's going on, somebody's gonna see it and they're gonna put it out there.
And one other thing, Glenn, I've already seen a half hour of Aurora this evening.
Already.
So,
Something's
move
happening.
to the old business. Anybody? Oh, go ahead.
The Kennedy Middle School's in Natick. Just,
Oh, okay.
Old business. Anybody wants to bring up any topics? Over to new business. Right. Well, now to the speaker. The talk title, as we mentioned before, Murder in the Observatory and the Enigma of Stellar Ages. Mackenna Wood is a postdoctoral associate at the MIT Kavli Institute. She attended grad school at the University of North Carolina at Chapel Hill, completing a doctoral thesis on measuring the ages of young planet-hosting star clusters. Mackenna is now working in the High Energy Astrophysics group at MIT, studying young stars in multiple wavelengths. Born and raised in Adirondacks, she is happy to be back in the North Country where she is free. In her free time, she enjoys hiking and crafting. The summary of the talk is measuring stellar ages is critical for understanding the formation and evolution of stars and planets over time. Unfortunately, the world's preeminent expert, Dr. S.T. Ellar, has been found murdered in her office. Join Dr. Mackenna Wood and a group of detectives to solve the case and explore the red herrings and false clues that come along with measuring stellar ages. Over to you, Mackenna. So.
All right. Hello, everyone. Thank you for the introduction. Thank you all for having me. Extra exciting because I wouldn't have known how to look for the aurora today, and I've never seen one before, so that was real cool. But yeah, my name is Mackenna. I'm going to talk about murder in the observatory and the enigma of stellar ages, and then there will be lots of time at the end for questions. I feel like I have already been sufficiently introduced, so I will skip on over this slide. And I got this letter in the mail the other day, and I don't really know why, because I am an astronomer, not a detective, so I can't help them with this. But it says, "Dear detective, I need your help. As you may have heard, Dr. S.T. Ellar, the world's preeminent astronomer, was murdered in the University Observatory 2 nights ago. Dr. Ellar was on the verge of publishing a revolutionary study on measuring the ages of stars, but the work has gone missing. Whoever killed the doctor must have stolen the manuscript as well. The police are stumped, so I'm calling on you to bring your detective skills to help. Come to the observatory to see the crime scene. I've also attached Dr. Ellar's latest notes."
Last notes.
Last notes. Lost my screen. Okay. Catching a murder and the key to understanding stellar ages rely on your help. Come soon. So these are the notes of Dr. Ellar to introduce us to what exactly we'll be talking about here, and that is stellar ages. So when we want to learn about how stars and planets change over time, we need to know what ages they are. So we know that stars and planets do change over time. We can see that from just looking at geographic evidence of the Earth. We know that our Earth has changed a lot over its roughly 4.5 billion year existence. And so and we can also tell from, looking at other planets in our solar system that they've changed as well. So we know that planets change over time. We know that stars change over time. But to understand exactly how that works, we need to look at other stars and planets because we are stuck with our one snapshot in time for our own. So to understand how these changes happen, to understand how stars and planets are how they are now, we have to understand how they got here. And these changes can't be observed directly because they happen over millions or billions of years, longer than the human study of astronomy, much less my career in astronomy. So in order to do this, we instead of observing one star and planet over its whole lifetime, what we have to do is observe a whole bunch of different stars and planets at different stages of this process. So essentially, what we would really prefer to do is on the left there. We want to look at the properties of these stars, their sizes, their temperatures, the properties of the planets, like their atmospheres or their mass or their size. And we want to observe that over the whole lifetime, millions or billions of years. But we don't get that. What we get is this. We get to look at a whole bunch of different stars, a whole bunch of different planets, at a bunch of various points. And try and figure out what's going on from this picture of many, many stars. And the problem here is this axis right here. When we want to put our stars on this plot, we want to plot them over time. Of course, we're not actually looking back in time. We are looking at a bunch of stars that are different ages. Not at different times, it's all right now. That's the only time we've got access to. So really what we mean by time here is age. We're looking at a bunch of different things right now at different ages. And that means that we need to be able to tell how old those things are right now. And that can be very difficult to do. When I drew the error bars nice and small so we could see what was going on there for the first, but this is more often what error bars on age look like. It's very, very difficult to get precise and accurate measurements of how old stars and planets are. And just as a sort of refresher on why those error bars matter, when we are looking at a plot like the top with error bars like that, those points could be anywhere along the error bars, which means that our point could actually look like the thing on the right, where there's not really very much of a correlation between the property that we're looking at and age. Could be kind of all over the place. Or we could actually be looking at something on the right here, where there's an extremely strong correlation between our property and age. And we really don't know, with error bars that big, it could be anything. So we need to figure out how to measure our ages really, really precisely and shrink those error bars down to where we can actually figure out what's going on. And the key to doing that, to shrinking those error bars, are stellar associations. Stellar associations are groups of stars that all formed at the same time and place. You might also know them as star clusters, which is a particular type of stellar association. So these are things like the Pleiades or the Hyades, where you've got one group of stars that all has the same age. And because we've got a whole bunch of stars that all have the same age, it suddenly becomes much, much easier to figure out what that age is. So when we are trying to measure the age of a star, we often get something like this. So these plots here, the lines show the property of a star changing, the property of a star at different times. So 10 million years, 20 million years, and 30 million years as a function of that star's mass. We call these isochrones, same time. So every point along this is what a star of a given mass would look like at a given age. And if we want to figure out how old a star that we're looking at is using a plot like this, well, we figure out the star's mass, and that gives us where we put it on the x-axis, and then we look at whatever property we're interested in, like the color or the magnitude or whatever it is that we're looking at. And that gives us where we are on the y-axis, and then we see which of these lines we are closest to. And hip hip hooray, we are 10 million years old. Of course, this is not how astronomical observations usually work. They have error bars. When we have the error bars in, it's very difficult to differentiate between those ages. This might be 20 million years old, or it might be 30 million years old, or it might be 15 million years old, or 35 million years old. Those error bars mean that we can't tell the difference. And that's a pretty big difference. From 15 to 35 million years old is over 100% uncertainty. So we would really like to do better. Of course, though, this star is really lucky. This star is in a region of this plot where it's actually fairly easy to tell the difference between those lines. It could have been over here, and then with those error bars, we wouldn't know if it was 5 million years old or 50 million years old. When we look at just one star, it's really hard to tell exactly what age it is. When we look at lots of stars, it becomes much easier to tell what age it is. So if we look at stars in an association that all have the same age, but a bunch of different masses, then we can figure out exactly what age we're looking at. So the original point is still up there, but now we can see with all of its friends that we know are the same age as it, that it must be about 30 million years old. So by having lots of stars and by having stars covering a large range of masses, we can figure out how old the stars that we're looking at are. So this is why associations are really the key to understanding stellar age. And this is why Dr. Ellar was looking at stellar associations when she was murdered. The particular association that Dr. Ellar was looking at is called the Mackenna Association. This is a group of stars that was discovered in around 2000. All of the stars in the association are active and bright, meaning that we know that it's definitely young. It's also very nearby. It's less than 100 parsecs away, so it's relatively easy to observe. It may contain stars with protoplanetary disks and planets, so it's really interesting. We want to study planets and how they form and evolve over time. And as an added bonus, it has been proposed as the origin point of the interstellar asteroid Kamehameha. It might have come from this association. So this is a really interesting association.
How is that known?
They calculated the kinematics of the asteroid and traced it backwards, and it ended up in the middle of this association.
Very nice.
It's a super interesting association. It's got a lot of cool stuff going on, but how old is it? We don't know. So this is the problem that Dr. Ellar was trying to figure out. And now that we are all caught up on Dr. Ellar's notes, we are going to head on down to the crime scene and see if we can put our detective skills to work and figure out both how old Karina is and what happened to Dr. Ellar. So when we get to the crime scene, the observatory here, there's a whole bunch of stuff going on. We've got blood on the floor, we've got books torn off the shelves and thrown around, we've got spilled water and everything. There's a lot of different clues that we might want to look at. So we've called in not one, not two, but 5 different detectives to take a look at this crime scene. And each of these detectives is going to look at a different aspect of the crime scene, at a different aspect of the stars in the Karina Association to try and figure out exactly what is going on. So we're going to start with our first clue, which is color magnitude diagrams. So when we first get to the observatory, Detective A notices on the chalkboard, there are a bunch of numbers written on the chalkboard. There's a list of association members with their colors and magnitudes. And there's also a schedule for the meetings that Dr. Ellar had on the day that she was murdered. 3 different meetings with T.L. Scope, one of her grad students, Dr. G. Alexi, a collaborator, and Dr. S. Pace, another collaborator that she was working on this paper with. And so Detective A takes a look at these numbers and as well as the meeting schedule. And since Detective A is a little bit of a hobbyist in astronomy, they know what they can do with color and magnitude information about stars. They know that the color and magnitude, or brightness, of a star changes over time following a predictable path. So this diagram here shows every star within, I'm going to grab my water bottle. Sorry. This diagram shows every star within 200 parsecs of the Earth as measured by the Gaia Space Telescope. These are their colors and magnitudes. And you can see that there's a whole lot of stars on there. This plot took forever for my computer to render. But also that most of them fall in one region of it. There's no stars down here in the bottom left corner. There's no stars in the top right corner. There's predictable patterns for where stars fall on this color and magnitude diagram. And these predictable patterns get even better because they depend on age. If we look at associations, so here if we look at one association, so we know that all these stars have the same age, it makes a very clear line across the middle of this. Looking at a second association, it makes another line that is slightly above the first line. So we know that these 2 associations have different ages, so the positions that they are on this plot depend on age. And we can use that to figure out how old a star is. We are going to measure the color and magnitude of all of our stars in our association and compare that to either evolutionary models come up with by people who do a lot more math than I usually do, or by observationalists who look at associations that we know the age of. And they're going to compare to that, and from doing that, we can figure out the ages of the associations that we are looking at. So Detective A knows all this. They can take that list, so we know here that the brighter stars, the stars that are closer to the top, are younger stars. So here we know that the association plotted in green is association 2 is brighter and younger than association 1. We're going to use that information to try and figure out how old our Karina association is. So Detective A takes the list of stars, all the colors and magnitudes that they found on the chalkboard, and they put them on a color magnitude plot and compare them against a couple different stellar evolutionary models, which is each of the panels, that's 3 different evolutionary models, to try and figure out how old it is. We can see from looking at this that it's a little bit difficult to tell. The numbers are kind of all over the place, but for the most part, they fall above 10 million years and below 40 million years. And so doing a little bit more sophisticated statistical analysis than that, Detective A finds an age of about 45 million years for this association. And so that is what Detective A finds the age of the Carina association is, using that list of stars from the chalkboard. Detective B also takes a look at the chalkboard, but they notice all this smudges down at the bottom, like something has been erased. And so they take a better look around the laboratory, and they find a list, a piece of paper where this list is fully typed out instead of just written on the chalkboard. And it's got a bunch more stars on it. We're not looking at just a handful of stars now, we've got a whole bunch of them. And so they're going to follow exactly the same procedure, but with these more stars. And so on this plot, they've got all the old stars that Detective A looked at in orange, but also a whole bunch of new ones added in blue. And they're going to follow exactly the same procedure using the slightly different model. This is the parsec model instead of the ones the other detective looked at. And they're going to do the same thing. And you can see, even looking here, that a bunch of these blue points are a little bit higher than where the orange points are. So what Detective B finds is that the association is younger than what Detective A found. They find that Carina is about 13.3 million years old, looking at a lot of these higher up points that are closer to the blue line on the plot. So we've got two detectives who have come in and look at two slightly different lists of association members and come up with completely different ages. We've got 45 million years and 13.3 million years. But there are other ways, other clues that we can look at in the observatory. And so we are going to look now at the motion in the observatory, or the motion of our footprints in the observatory, as well as the stellar motion. Detective C comes on in and finds a note left near those bloody footprints on the ground. Excuse me.
What is the proper motion?
No. Sorry. No, that's okay. No, that is not the proper motion. I will tell you what it is in just a second. Detective C finds this note on the ground. They also find all these bloody footprints. And Detective C, taking a look at the footprints first, measures the distance between the footprints and uses those to estimate that the whoever ran out of here and left these footprints on the ground must be over 6 feet tall. There's only one person on that meeting list who is over 6 feet tall, and that is T.L. Scope, the grad student. So Detective C thinks that we had better take a look at T.L. Scope for our suspect. Did forget to mention earlier, Detectives A and B both agree that we should take a look at Dr. S. Pace as our suspect, as they had the last meeting with Dr. Ellar that day. So they think Pace is good for it. But C thinks that we should take a look at Mr. Scope, but also notices this note on reversing the stellar motion. And Detective C, also being a bit of an astronomer, knows that stars are not still in space. They move around. In particular, the stars in our galaxy are orbiting around the center of the galaxy, following a path something like this one here. This is for our sun over a period of a few tens of millions of years. I forget exactly. I think it's about 50 million years. Going around and around the center of the Milky Way. And so this really interesting idea that stars move over time can actually be used to help us find groups of stars that formed at the same time and place, because they will have similar velocities to each other because they all started at that same point in the galaxy. And so you can try and figure out when two stars formed. So we can try and sort of trace back that motion of the stars and see where they formed. Two stars that start in the same associations, eventually they'll get pulled away from each other by the galactic gravity. And so stars that start out really, really close to each other will end up further apart the longer time goes on, unless they are close enough that they are gravitationally bound, which is a different story. Most of our associations are not gravitationally bound. They're going to spread out over time. So this shows two stars that start in the same association. over a period of 500 million years. They start at only 12 parsecs away from each other. By the end, they are 730 parsecs away from each other. That is far outside of what we would consider our stellar neighborhood. Usually our stellar neighborhood's like 100 parsecs. So we can use this in our favor. We can take stars that we know started in the same place and trace their motion backwards. And by doing that, we can try and figure out where they all started. So to actually do this with astronomical data, what we do is we measure the proper motions and the radial velocities of the stars that we're looking at, and then we convert that into a new three-dimensional coordinate system, which is shown here. So this is our galactic coordinate system. X goes towards the center of the galaxy, Y goes in the direction of galactic rotation, and Z goes out of the plane of the galaxy. The sun is at the origin here, and all other stars we calculate around it. And this is really important because it lets us put stars in sort of the idea of the galactic frame. If we are only looking at stars on our sky using proper motions and radial velocities, then stars that are really close to us will look like they're really far apart from each other when actually they're close to each other. They just look close to us because of projection effects. So this converting to this galactic coordinate system is really important when we're trying to get an actual idea of the galactic motion of these stars. And so Detective C measures the velocities of all of those different members of Carina that we found the list for, and plots them here. The arrows are the direction they're moving now. So if you sort of extrapolate the arrows backwards, you can figure out where they started up. And you can extrapolate this backwards for tens of millions of years and try and figure out when all of the stars were closest together. Because when they were closest together, it must have been when they all formed from that same molecular cloud. They formed and then they spread out. So when they're closest together must be when they formed. And so Detective C does this and looks at the results. And here the y-axis is the mutual separation between the stars, whereas the x-axis is the time backwards. So this edge is where we are now, and then we're moving backwards. And Detective C finds that these stars were all closest together at about 28 million years ago. So this association must be at least 28 million years old. Now, the calculation through the, you have to integrate over the galactic potential to do this moving backwards through time thing, and it gets really difficult to do it out for a long period of time. So after about 30 million years, it starts to get a little bit more difficult to calculate. We're a little bit less sure. So we're just putting a lower limit here, but we are saying it is at least 28 million years old based on the motion of the stars. And so that is what Detective C finds. They look at this motion, they look at the footprints, they think that DL Scope is our murderer and that Carina is at least 28 million years old. But we've got even more to look at. So for our third clue, detectives D and E are going to take a look at the computer screens over here, and they're going to look at lithium. So detectives D and E, they take a look at their computer screens, they find what Dr. Ellar had up, what she was working on right before she was murdered. They also find this glass spilled and broken with a fingerprint on it. They do some testing and determine that that fingerprint belonged to Dr. Alexey, G.L. Alexey, and think that this is evidence that maybe he was having a fight with Dr. Ellar, knocked over his glass while he was angry. They think they should talk to Dr. Alexey a little bit more. But then they take a look at the actual computer screens, and they see a bunch of spectra of different stars from the association, a bunch of lines that tell us how bright the light is at specific wavelengths. And they see plotted this plot here, which shows a dip in the brightness of the light at a very specific wavelength. And being astronomers themselves, for some reason, the detectives know that that particular wavelength where that dip is means that it's caused by lithium. And so they know that this is lithium that Dr. Ellar was looking at, and that lithium is a really interesting tool for determining stellar age. And that is because lithium is formed in, all stars form with some amount of lithium in them. It came from the Big Bang, and now all stars have at least a little bit when they are very first formed. And then that little bit of lithium that they started out with gets used up over time through a fusion process, the lithium proton-proton chain, which involves a bunch of different reactions. But the important part here is that you start out with lithium and you end up with helium and no lithium. So it uses up all of the lithium. And this reaction only occurs at temperatures of hotter than 2.5 million degrees. So this only happens once the core of your star gets to 2.5 million degrees. And that means that we can use it kind of like a clock, because stars heat up over time. Did you have a question?
Is this observable through the spectra of the star?
Yes. And so this lithium can be used kind of like a clock. And even more specifically, we can use lithium like a clock the best in certain kinds of stars. So stars that are smaller than our sun, the stars that are smaller than about half the size of our sun, are fully convective, which means the whole entire star works like a convection oven or a lava lamp. Stuff is at the center, gets hot, rises up, cools down as it rises away from the heat at the center, and then falls back down in. And so you have actual material moving around in the star, which is key, because it means that all of the lithium in the star at some point moves into the center and gets to that really hot part and burns up. In stars like our sun or bigger stars, you have the center of the star is what we call radiative, meaning that instead of the actual material moving, it's just photons moving around. And so photons are bouncing around and, chain reactioning into each other, but the actual plasma of the star is pretty much standing still. And so in radiative regions of a star, stuff doesn't move around very much. So all of the lithium at the center is going to get burned up, but new lithium from the surface isn't going to get brought into the center. It's going to stay at the surface. So in these small stars, we're going to burn through all of the lithium real quick. And in these really big stars, you're not going to burn through all of it. You're going to have some of it left over at the surface because it can't reach that center part where it's really hot. And this is really important because it means we have a dividing line between the stars that are hot enough to burn their lithium and also low mass enough that they burn all of their lithium, and the stars that are too hot or too big so they don't burn their lithium, or too cool so they don't burn their lithium. And so that's what is going on here. So we get a relationship between the mass of a star. This is color on the bottom, but it's basically the same as mass. Big stuff over there, little stuff over here. And their age and how much lithium they have in them. So really young things have lots of lithium. If we look at a really young association, like the one plotted in blue, pretty much everything has a whole bunch of lithium. If we look at an old association, like the one plotted in red, that's actually the Pleiades. Only the really big stars where the stuff on the surface can never get to the center have anything left. Everything else has been burnt. So we can use this as a clock and try and figure out, based on which stars have lithium, how old an association is. And so that's what Detective D does. Detective E gathers measurements of lithium within our association members and then compares them to other associations that have known ages. So here they're comparing to Tucana horologium and Beta Pic, and the red points are the ones that we are looking at. So we can see that our red points mostly overlie the gray square points. So it looks like our red association is about the same age as the gray association, which is about 24 million years old. So Detective D thinks, based on this, that Carina is about 24 million years old. Detective E takes a slightly different route. Detective E really focuses in on those very small stars where the lithium all gets burnt very quickly. And in those very small stars, looks for the dividing line between the smallest, coolest stars that haven't reached 2.5 million degrees yet, and the slightly bigger ones where their core is 2.5 million degrees, and so they've burnt through their lithium. And so in this plot, the dots are stars, members of Carina that do have lithium, and the X's are members of Carina that don't have lithium. And we can find the magnitude where there is a dividing line between those things. That's marked in black there. And comparing that to models, we can figure out that if as up here, all of our stars that are brighter than 6.8-ish don't have lithium, and all of our stars that are fainter than that do have lithium, then our association must be about 41 million years old. And so this is what detective E does to figure out how old the association must be, using lithium just like detective D. So now we've got all of our detectives have taken a look at all of the clues. They have each come to a different conclusion about the age of the association and about the identity of the murderer. So now we have to figure out what to do with all of those different pieces of information to actually solve the case. So here's the summary of what we've got. Detective A and B both looked at color magnitude diagrams. Detective A found 45 million years, Detective B found 13 million years. They both agree that the murderer must be S-Pace because they had the last meeting. Detective C looked at the motion of the stars and finds that it must be at least 28 million years old and thinks that TL Scope is our murderer. Detectives D and E both looked at lithium. D found it's 24 million years old. E found it's 41 million years old. And they both agree the murderer must be G. Alexey. So what are we going to do? We're going to go and take a slightly closer look at all of the information that all of our detectives look at, starting with Detective A. If we look at Detective A's analysis, they took the colors and magnitudes and they compared them to different stellar models. This is just one of the models that they compared it to. What are some potential problems with this? Well, first off, it's got 9 points on there. We're doing an analysis based on 9 stars, which is not a lot of stars. Additionally, 11, I guess it's 11 stars. The stellar evolutionary models that they used didn't include magnetic fields in them. So in the last 15 years or so, astronomers have figured out that magnetic fields are really, really important for determining the color and magnitude, especially of these young stars. But Detective A hadn't heard about that, so they used older models, models that don't have magnetic fields in them. Those are some of the problems with Detective A's work. What about Detective B? So Detective B included a bunch more stars, but the risk of including a bunch more things is that some of them might actually not be in the association. And that was exactly the case here. 3 of the new stars that Detective B added are non-members of the association. They are actually older stars that look, that are in, sort of the same place, but they're not actually part of this group that all formed at the same time. They also compared against non-magnetic models. They also hadn't heard the updated research. And their fitting method really heavily weighted the stars that are high mass stars, the stars that are over here. And those stars are a little bit harder to tell because sort of all of the model lines come together at those points. So it's a little bit harder to tell based on only these stars how old it is. We kind of want to include the whole thing so that we get this region down here where they're really far apart and it's easier to tell. So we can fix these problems with both Detective A and Detective B all at once. We can use Detective B's list with more members, but remove the ones that we've since found out are not members. We could also compare against a magnetic model. And that gives us this. This looks a lot better. It still has a lot of scatter. This is up on the blue line and this is down on the purple line. But most of the stars here are in our 20 to 50 million year range. We can do even better than this though. We can look on our own for different star measures and not rely on the piece of paper we found in the observatory. And so we can use a new membership list based on new data from the Gaia Space Telescope. With really strict cuts to make sure that we don't let in anything that's not actually a member, compare against our new models, and that gives us a lot more stars to look at. The Gaia Space Telescope is great, looks at tons of stars, so this gives us a lot more data points. And with our a lot more data points, with our good magnetic models, we can say that everything looks like it's between the green line and the red line. So we are between 20 and 40 million years old here. So this is our updated analysis. Combining detectives A work and detectives B work, we find that we are about 20 to 40 million years old. We're going to leave detective C alone because theirs was just a lower limit. It actually is relatively consistent with the rest of them because it's just a lower limit. And we're going to go down to detectives D and E. Detective D looked at this plot of the lithium in Carina at different masses. And there are a few problems with this. One of those is that they were using that old membership list that had a few stars that were not actually members on it. And so the analysis here is really based heavily on these 3 stars. These are the ones that distinguish between the gray and the green. These 3. And one of them is not a member. One of the other ones is kind of iffy. We think it's still a member, but it's a little bit iffy. So if we're basing our whole analysis on these 3 points, and at least one of them is wrong, then our answer isn't going to be the best it could be. The bottom here is also spectral type. And spectral type can be difficult to calculate. It's not a direct observational. And we like to compare things to things that are directly what we see with the telescope. We don't have to do any math in between where we might have additional uncertainty added in. They also used mostly stars sort of in this range. And those are those stars where I said they have the radiative part at the center. So not all of the lithium gets burnt up right away. It's a little more difficult to predict how quickly the lithium will get burnt up because you need to be able to know how fast stuff is moving from the outer part into the inner part. So because of that, we like to focus more on the stars on this end of the plot. So we can do that. We can add in all of the stars that Detective E looked at, which adds in a bunch of stars on this side of the plot. We can remove one of those 3 stars from up there that we know isn't a member, and we can put this in terms of a direct observable color here. And doing this and then comparing against those same associations that Detective D was comparing against before, we can say, okay, so now are we closer to the red one, or the orange one, or the yellow one? Clearly not the yellow one, because the yellow doesn't go up at all down here. It also looks like it's not the red one anymore. When we have more points over here, we can see that beta pic, the youngest association here, goes up earlier than our points here, which lie mostly on top of the orange squares. So when all of our points are lying mostly on top of the orange squares, that suggests that it's about the same age as Tucana Horologium, which is 40 million years old. There's still some weirdos in there. It's still a little bit hard to explain those two. They're kind of near an orange square, but much more closer to the red points. But overall, with our many more stars here, we can say that there's a much better idea that we are looking towards 40 million years than any of the other ages from before. So now that we've taken another look at all of our detectives' work, we can say that the detectives A and B say 20 to 40. Detective C says greater than 28. Great, that's consistent. We've got a range that we can limit it to. And detectives D and E both say 40. So everyone agrees that it could be about 40 million years old. We have all come to a consensus using 3 different independent methods of figuring out the age of this association. Everyone agrees that it can be 40 million years old. Our detectives also bring in all of our suspects for questioning. And when Dr. Alexey was asked about the broken glass with his fingerprint, he freaked out and confessed the whole thing, was having a fight with Dr. Ellar about the results of their work. So our detectives have found both the age of our association and our murderer. Our case is solved. Some of the conclusions here is that determining the ages of stars and star clusters is really hard. There are lots of different ways you can look at the same set of stars, lots of different types of data that you can use, different methods, and they sometimes produce contradictory results. And so getting an age like this is sort of a balancing act between including as many stars as you can so that you have a really good full picture of the association, but also not including a bunch of stars that aren't actually members. And finding, sort of more generally, finding the answers to scientific questions like this is not usually straightforward, this data means this answer. It's often a lot more complicated than that. There are usually multiple different explanations for a particular data set, and different methods or different data sets of the same thing can tell you different things. So those are the key points. As a note, our intrepid detectives are all based on different published papers looking at the age of the Mackenna Association. These are those. I am Detective E. And yeah, take time for questions.
Okay.
Yeah.
I'm sort of ramping on my astrophysical chops late in life. I'm curious to know, of the different attributes of stars, how would you rank like the smallest error bars to the larger, just like the first, few? You mentioned mass, for example.
Yeah, so mass has relatively large error bars because we cannot directly weigh a star. We can measure the color and the brightness of that star and then compare it to evolutionary models for what we expect a star of that type, that color, and that magnitude to be the mass. So mass has pretty large error bars because there's a lot of steps there. The direct observables always have the smallest error bars, and of those, things like color and magnitude tend to have much smaller error bars than spectral things like the amount of lithium in a star. Yeah, I guess, does that answer your question?
Yeah.
Yeah.
I read somewhere, I'm not sure where, that lithium, although it's not radioactive, it's not particularly stable either, that even the heat of a star is enough to rip apart the nucleus. Is there any truth to that, or was I misinformed? And if there is some truth to that, how does that fit in with these reactions? Because the lithium needs to stick around long enough to react.
Yeah, so, I mean, it kind of depends. So we are looking at, okay, so first, we are looking at a very specific type of lithium. We're specifically looking at lithium-7. I don't know if there are other isotopes of lithium that are less stable than this one. This one is pretty stable until you get to 2.5 million degrees. And at 2.5 million degrees, then it starts to break apart. So it does break apart in the cores of stars, even relatively small stars that are like 1/10 the size of our sun will get hot enough to rip apart lithium in their cores, but only in their cores, really, and the Earth is not going to be that temperature. So it is stable enough for our purposes, at least the isotope that we're looking at. I am not familiar with any other isotopes.
The convection that does mixing,
Mm-hmm.
does it reach to the surface in most stars? I've been told, I'm not sure it's true, that the sun, the surface is still zero-age main sequence concentrations.
That is, I think, probably true for the sun. So it depends on the mass of the star. So those really low mass stars are fully convective. Everything's getting mixed all the way through. Stars like our sun, they have their radiative zones and their convective zones. I think it's possible that the surface itself mostly gets left alone. And then even bigger stars, it's actually reversed of our sun, where the convective part's in the middle and the radiative part is on the outside. So your outside's never really going to change because your outside is the radiative
The
part.
rotation of the star makes a difference also. It does change. The Tassel wrote a book about this.
Yeah, it changes the way the convective mixing occurs. It doesn't have a direct effect on the abundances.
Thank you.
So I noticed at least one of your detectives was comparing again to the other associations, so the Pleiades and other.
Yeah.
And, one of those was 124 million years.
Mm-hmm.
Where did that confidence come that you could go to the third digit when here it looked like we were either 20, 40, 100, and that's sort of the best we could do?
Yeah, so I will say that for the version of this talk that I'm giving now, I much simplify the numbers. The precise number that we have for Mackenna, combining all the different types of analysis, is 41 plus or minus 3 million years. The age for the Pleiades, that was 120 that I quoted there, that's about plus or minus 5-ish, I believe. And it's about the same for the other associations we're looking at. Those are what we call benchmark associations. You know, the Pleiades you can see with your eyes. These are things that have been studied for a really long time using a bunch of different methods, a bunch of different data sets. And so by putting all of that together for these benchmark associations, we get pretty precise age measurements for them, and then that lets us compare other associations to them. Does that answer your question? Yeah.
One of your graphs a few slides back had milliamps as the units.
Not really.
I think I had milli-angstroms. Yes,
Oh.
milli-angstroms, and the little O
Can't do that.
gets messed up on PowerPoint.
Isn't a legal SI unit.
But yeah, that is milli-angstroms.
No. Wow. You mean nanometers?
No, I mean angstroms.
But milliangstroms, mean thousands of an angstrom?
Yes,
Oh,
so we are measuring the like the integrated area over the line. So we have a line that occurs at exactly
you're looking at the thickness of the
6708
line, okay.
nanometers, and then we are looking at like the integrated area of that dip in the line, and that is what we are measuring in milliangstroms.
It should be picometers.
Correct, for SI.
Yeah, and
So looking at this, you mentioned that the two stars seems to be younger, matching big pictorials. Have you considered possibilities that there is some successive star formation within the same association? I mean, how big the association is, I'm not sure how big it is. And while in the star forming region, you could have like successive star formation, and there's also research on feedback, like jets and some contamination, for example, of lithium or non.
yeah. Yeah.
Just
That is a great question. So the amount of age spread, which is the term we tend to use for it, within an association, so the stars we know are not all literally exactly the same age. There is some amount of age spread. But whether that is, you know, like less than the possibility that we could measure, like less than 1 million years, or if it's like 2 million years, or even like up to 7 million years is about the largest estimates we've got for age spread, is an open question. It's a really interesting question. It's the question I am working on my next research for. For Carina. For Carina itself, it is a relatively small association. So compared to something like Scorpius Centaurus, where we know that there has been star formation occurring in Scorpius Centaurus over a period of about 20 million years, continuously in different parts of the association at different times for about 20 million years. Carina isn't big enough to have had that. So for Carina, we think it's probably a lot smaller. Based on just what we see here, if you look at the lithium levels, it might be as high as like 7 million years of spread within the association. But it's also entirely possible that just like those stars are really weird, or that those measurements are slightly wrong, or something like that. So we can't exactly rule out that there is up to about 6 or 7 million years of age spread within Carina, but we also, you know, probably at least some of this scatter is from uncertainty or experimental error or something like that, and not entirely from age spread. So it's probably less than that, if that answers your question.
Hi, online here. Can you hear me okay? Okay, so I just wanted to know, this is the first time I've heard about this lithium phenomenon. Is there a name for like a dividing line between the fully convective and the stars that are not fully convective? Is it somebody's name attached to that, or do we just refer to it as fully convective, etc.?
I've always just referred to it as the fully convective boundary. I don't know of any particular name for it. And then the specific name for the lithium dividing line is the lithium depletion boundary. And then for higher mass stars, you look at the lithium abundance as a function of age.
And so is there, where does our favorite star lie in that? Do you describe this dividing line in terms of numbers of solar masses?
Yeah, so you could describe this in terms of numbers of solar masses. One is here-ish. It's roughly between like 1.5 and 2 on my thing, if I am remembering correctly. And then on the right side of the plot are late M dwarfs. So like after 3.0, we are less than half the size of the sun. And then you get bigger than the sun. I don't think this goes up to anything super massive. Like I don't think I've got any O's or B's on here. I think I've got some F's on here as the biggest stars that I've got on this particular plot. Karen is too old to have O or B stars.
Thank you very much.
Mm-hmm.
Okay.
Are there other variables that could you name some other examples of variables you would use to, I don't know what you call this technique, kind of partition them into, you're sorting stars kind of is what you're doing.
Mm-hmm.
What other variables could you use to sort?
So as far as sorting by age goes, color and magnitude and lithium are the big ones. Lithium is my favorite one because it's the most accurate. You can also do it by rotation rate, although it is much less accurate. Stars that are younger spin really fast and then they slow down over time. It's a little more complicated than that. They actually start slow, speed up, and then slow down. Which makes it a little bit more complicated to get an age from that because the slow could be on either end.
Is that measured with Doppler or something?
No, you can actually measure that using the light curves of the star, so you just measure how bright it is. And since most stars, especially these young stars, have spots on them, your light curve will look like this as your star rotates around and the different spots come into view or go out of view. So we use the telescope TESS, which was designed for looking for transiting exoplanets, has actually been revolutionary for the field of, it's called gyrochronology, for looking at how old these stars are based on their rotation speeds, because we get light curves for like every star in the sky practically. Yeah. Okay.
Thank you. Is there something, a measurement capability on the horizon that you can see that you think would, like, if we could just do this, then it would revolutionize, our ability to close an error bar on a key metric or bring another metric on that could be interesting?
I don't think there's anything like revolutionary like that. I think in this field in particular, it's often kind of a slog. We just got to keep getting more data and more associations and figuring out the ages of those associations and adding them to our benchmark list, and then we can find more and then we can compare them to our more benchmarks. And so I showed, this is the list of benchmarks. This is like a pretty typical list of benchmarks right now. We've got 24, 40, and 120, roughly. What if it's 80? How do we know if it's 80? So we want to keep finding more and more associations to fill in this gap, and then we can compare to things at a whole range of ages to get better ages. And so it's kind of just like a slow, gradual increase for this particular field. Telescopes like Gaia, which launched, its first data came out in 2016, have been absolutely revolutionary because you used to not be able to get the colors of this many stars. Getting just the colors or the brightnesses of as many stars as we've gotten here, as many really faint stars as we've gotten here, these are like 21st magnitude, was very difficult. And so having a space telescope dedicated to literally just measuring really precise colors and magnitudes was really great for this. And there are some other survey missions like that give us the data, and then we can do that. So I guess those are kind of revolutionary. Yeah. Okay.
So this is the close of the meeting. Next meeting is November 14th. See you there.
Very good.
Thank you.